Hello everybody, today I will review some fundamental properties of Hilbert spaces based on the appendix of the book Les maths en tête Analyse by Xavier Gourdon. A Hilbert space H is a vector space endowed with an inner product, so over the real, this is a symmetric definite positive bilinear form. Over C, one has to choose a convention whether the sesquilinear form is linear or antilinear with respect to the first or second variable, and it will clutter the notation with real part, imaginary part, complex conjugate modulus, which bring nothing to the understanding, so we'll assume that H is a real Hilbert space. To an inner product is associated a norm, and the Hilbert space is complete with respect to the following distance. Also, since there are proofs that are specific to the finite dimensional case, we will assume that the Hilbert space is infinite dimensional. Let us recall two crucial properties before we start. So the Cauchy-Schwarz inequality for all x and y, inner product x and y is smaller than the product of the norm, and the parallelogram identity. So we can easily go from the left-hand side to the right-hand side. So norm squared of a sum plus norm squared of a difference. By definition, this is x plus y inner product with x and y, and here x minus y inner product with itself. The cross term cancel each other, so 2 inner product x and y, and here minus 2 inner product x and y. This video can in fact be called the theorem of projection on a closed convex subset and its consequences, since 2, 3, 4 are consequences of 1. Let C be a non-empty closed convex subset and X a point. The function which to Z in C associates the distance between Z and X has positive values, so it admits an infimum, which is by definition the distance between X and the subset. The theorem says that this infimum is in fact a minimum. So a drawing is always a very special case because it is finite dimensional. So in that case, one can consider the closed ball with center x and radius the distance plus something. So this is a closed and bounded subset, and its intersection with a closed subset is still closed and bounded. And thus, a continuous function reaches its minimum on this compact subset. But the theorem still holds in infinite dimensional spaces, and it is, for example, used in the theory of elliptic partial differential equations to show existence and unicity of solutions. So the first application of the projection theorem is, given a closed linear subspace, the decomposition of the Hilbert space as a direct sum of F with its orthogonal complement. So we'll prove the theorem in finite dimension and mention how it is generalized. So let B be an orthonormal basis of F. One can define as follows the projection map on F. It is such that X minus its projection is orthonormal to every vector of B, so it is orthonormal to F. Hence, an arbitrary element can be decomposed as an element in F plus an element in F orthogonal. What the theorem allows is to define this projection on F regardless of whether F is finite or infinite dimension, as long as it is a closed linear subspace. So a first corollary of the decomposition of H as a direct sum of two orthogonal subspaces is the Riesz representation theorem. For any linear continuous form, there exists a unique vector such that the linear form is inner product with A. In the last section, we introduced the notion of Hilbert basis or orthonormal basis. So let En be an infinite orthonormal family of vectors and F the vector space of its finite linear combinations. We consider the projection on closure of F. The projection formula extends to the infinite dimensional case, so we will show that this infinite sum is convergent, and the sequence of coefficients is in fact square summable. So if an orthonormal family generates a Hilbert space in the sense that the closure of its span is equal to H, then it is called a Hilbert basis. And any vector decomposes as a possibly infinite linear combination.
So let C be a non-empty closed convex subset and X a point. The distance between X and C is the infimum or greatest lower bound of all distances from Z to X, where Z varies over C. The theorem says that this infimum is in fact a minimum, and more precisely that there exists a unique point xc in C such that the minimum is realized. So this looks obvious in this picture because C is compact. So let me give an example where it is less obvious. So imagine that we have an infinite family of orthonormal vectors that I call ui in N, and let me denote C1, C2, C3, the endpoints of those vectors, etc. So the distance of C1 alone to X is 1. If now I consider the segment from C1 to C2, it reaches a minimal distance to X at some point here in the middle. If I continue and I consider the convex subset generated by U1, U2, U3, it reaches its minimum in some point here. So the idea now is to consider the convex subset generated by this infinite family of vectors. So here I do convex combination where the coefficients are positive and sum up, add up to 1. So we have points whose distance to X converges to a minimum. But the question is, does there exist a point xc in C such that the minimum is realized, is reached, the distance is minimal? And in fact, the answer is tricky because it depends on what we mean by convex subset generated. Here, if we only allow finite sum, then C will not be closed and the theorem will fail. So what we really need is C to be closed. And as a closed subset of complete space, it will be complete. So what we are replacing compactness by completeness and convexity. So in section 4, we'll discuss in more detail closed subset, subspace of infinite dimension. So here we have characterized the orthogonal projection as the unique element in C that minimizes the distance. So there exists a second characterization in terms of direction and angles. So for all z in C, I can consider this vector from xc to z, and I'm doing this, its inner product with this vector x minus xc here. And the condition says that the inner product is negative, and the geometric interpretation is that the angle is greater than pi over 2. If I consider the set of vectors whose angle with x minus xc are exactly pi over 2, it is the orthogonal complement. It is a hyperplane of vectors that are orthogonal to x minus xc. This hyperplane cuts the Hilbert space in two parts, and what this condition says is that every point in the convex subset, they are in one of the half space, hyperplane included. In fact, in section 2, we'll see that the most important things happen in the width of a stroke. So when C is a vector space itself, it will be included into this hyperplane. And finally, before I start with the proof, when X is inside C, then the minimal distance is 0, and it is reached at a unique point xc equal x. So let me now start with the existence of this orthogonal projection. So let us denote delta, the distance between x and c. If I add a positive number to delta, it will no longer be a lower bound of all distances. So there will exist an element in C such that the distance between Z and X, so an element Z in C, whose distance is smaller than this quantity. If I repeat this argument for a sequence of strictly positive numbers which converges to 0, I will obtain a sequence of points, as known as minimizing sequence, whose distance to X converges to delta. So here it's a convergence of positive numbers. But what I want to show is that this sequence of points, this Zn, also converges. We'll do this by proving that it is Cauchy. Let me consider, so for P and Q, those two vectors, so x minus zp, x minus zq. Here I have their sum norm square plus the difference norm square, and by the parallelogram identity, it is equal to 2 times the first vector square plus 2 times the norm of the second vector square. So here I have x plus x, I factorize the 2, and here I have z minus zp minus zq. With the 2 factorized power 2, it gives 4. And now I recognize here a convex linear combination, 1/2, 1/2. So this is a point that is in the convex subset. Here I have x and x cancel, remains zq minus zp, and same right-hand side. So because this point is in the convex set, the distance to x is greater than delta. If I multiply by 4, it preserves the inequality. And if I multiply by -1, I will have -4 times this, smaller than -4 delta square. I distribute 2 delta here, 2 delta here. And now let us consider those two quantities. Since the sequence Zn was chosen such that its distance to x converges to delta, it means that this can be made arbitrarily small and similar for here. So for all epsilon, there exists a n such that for p and q greater than n, this is smaller than epsilon, this is smaller than epsilon. So it means that this sequence is Cauchy. And because H is complete, a Cauchy sequence has a limit, and since C is closed, the limit is in C. At this step, when we choose the minimizing sequence, there are many possibilities. Suppose we choose 2 minimizing sequences with limit y and z in C, which have minimal distance to x. We can now consider a new minimizing sequence, which for even terms is z and odd terms is y, and we just alternate between those two. We repeat the same procedure and obtain that it is a Cauchy sequence. It means that the distance between z and y can be made arbitrarily small. So more explicitly, let us write the parallelogram identity for the vector x minus y and x minus z. As previously, this convex linear combination is in C, so its distance to x is greater than delta. And here we have norm of x minus y equal delta, so delta square plus delta square times 2, so 4 delta square minus something greater than delta square is negative or 0. So the norm of z minus y has to be equal to 0. Let us give an alternative formulation of what we have done. So we have our closed convex subset and our point x. We are considering a family of closed balls, so with radius delta plus epsilon n, closure, and I take the intersection with C. So let me call this intersection Cn, which is closed as the intersection of two closed subsets. And now if this sequence is decreasing, then we will have the property that this sequence of intersections are nested, so they are included in one another. So we'll now use the parallelogram identity to show that in addition, their diameter goes to 0. So let me take z and y in this intersection. So now they do not satisfy this condition, but their distance to x is smaller than delta plus epsilon n square. And similarly for this term. This term, we had already seen that it is smaller or equal to minus 4 delta square. So now let me expand here. Delta square plus 2 delta epsilon n plus epsilon n square. So I have delta square plus delta square times 2, it gives 4. So it cancels with this term. Now I have 2 delta epsilon plus 2 delta epsilon times 2, so a delta factor of epsilon n. So what we have is that if this sequence of epsilon goes to 0, then the maximal distance between any 2 points is also bounded and goes to 0. And now we recall this equivalent characterization of completeness, which says that if we have a nested sequence of closed subsets whose diameter goes to 0, then their intersection is non-empty and in fact reduced to a single point. And we can also compare to the situation where C is not convex but instead compact. It has similar kind of characterization. So we recall the finite intersection property, which says that if we have an intersection, so not necessarily countable, but intersection of closed subset of a compact set, if it is empty, then there exists a finite set of indices such that, finite, such that the finite intersection ICN is empty. So we just use the usual characterization with open subsets and take the complementary. But here, if I denote n0 the maximal index in I, because those subsets are nested, this intersection will in fact be equal to Cn0. And because epsilon is positive, this intersection is non-empty. So by contraposition, every finite intersection is non-empty. It implies that the whole intersection is non-empty. But we cannot guarantee that it is reduced to a singleton. So we have a sequence of balls that are nested intersections. So when we, in terms of sequence, we have a minimizing sequence, and here it says that there are different possible adherence values. So you can extract different convergence subsequence, but they may converge to different limits. So let us now show the equivalence between the two characterizations of the orthogonal projection. So let Y be in C and satisfy the second condition. We see that this kind of inner product appear in the norm square of a sum. So this suggests to consider z minus x norm square. We do minus y plus y and then expand. I have z minus y square minus 2 times the inner product, and we see that it is exactly the inner product we want, plus x minus y square, norm square. This is negative, so times minus 2 it becomes positive. So we have the sum of 3 positive terms, which is of course greater than the last term alone. If I take the square root, I obtain that the distance between y and x is smaller than the distance between x and z for all z. This means that y realizes the minimal distance, and we have seen that it is unique. So y is equal to xc. Conversely, I write the fact that xc realizes the minimum, and I take the square. So at the moment, it's the same calculation as before, except that we had a y. So we do minus xc plus xc. We do the same expansion, and this time simplify. We see that we get almost what we want, except that we have an additional term. And we'll exploit now the fact that here z minus xc appears with power 1, and here it appears with power 2. So we'll consider, in fact, a family of points, so those convex linear combination with parameter lambda.
This inequality also holds for z lambda, and if I do z lambda minus xc, so I do minus xc, I'm left with lambda factor of z minus xc. And here I do have lambda with the power 1 and here lambda with the power 2. I simplify one of the lambda and it does not change the direction of the inequality because lambda is positive, and obtain a term that is independent of lambda, and here lambda times something. So with the limit lambda goes to 0, this term will go to 0. I'm left with what I want. In this second section, let us prove some fundamental properties of the orthogonal complement. Let A be a subspace of H. The orthogonal complement of A is the set of vectors Y which are orthogonal to every element of A. First property, the orthogonal complement is a closed linear subspace. So there is a symmetric statement that I leave as an exercise, which says that the orthogonal complement of A is equal to the orthogonal complement of the closed linear subspace generated by A. Second statement, if F is itself a closed linear subspace, then the Hilbert space decomposes as F direct sum with F orthogonal. Moreover, the map which to X associates the orthogonal projection on F, which is indeed a closed convex subset, coincides with the map which to a decomposition projects on the first component. And finally, when F is closed, it is equal to its double orthogonal complement. If F is not closed, then the F orthogonal is equal to its closure. And last property, if F is a linear subspace, then one has the equivalence F dense in H if and only if F orthogonal is reduced to 0. So let us now show that the orthogonal complement is a closed linear subspace. So let y1, y2 be in the orthogonal complement, and let us consider a linear combination. By linearity of the inner product with respect to the second variable, one has this expansion, and because y1 and y2 are in the orthogonal complement, this is 0, this is 0. It means that the linear combination is indeed orthogonal to every element of A. Let us now show that it is closed by considering a convergence sequence with limit y. So each element is in the orthogonal complement, so the inner product is 0, limit of 0 is 0, and by continuity of the inner product with respect to the second variable, one has that limit of those inner products is equal to the inner product of x with the limit of the sequence. So the continuity stems from the Cauchy-Schwarz inequality. So if we look at the difference of those two terms, by linearity with respect to the second variable, it is this inner product, and by the Cauchy-Schwarz inequality, it is smaller than this product of norms. So when yn converges to y, this term converges to this term. One can reformulate this in a more abstract way by considering for each x in A, the linear map which to y associates inner product x and y. It is a linear map, so the kernel is a vector space. And it is a continuous map, so the pre-image of 0, so the kernel, pre-image of a closed subset is a closed subset, and the intersection of closed vector space is a closed vector space. Second property, we need to show that if F is a closed linear subspace, then one has the direct sum. So first property, the intersection is reduced to 0. So let us consider an element in the intersection. It is orthogonal to itself. So by the definite positiveness of the inner product, it is equal to 0. Let us show that the direct sum generates H. So let X be an element in H, and XF its projection on F, which is, as we said, a closed convex subset, non-empty closed convex. Let me sketch. So one has, by the first section, those two characterizations, and in order to take advantage of the linear structure of F, we'll use the second characterization. So we have xf, an element, the projection, and here I have written the orthogonal complement of x minus xf. So the hyperplane of vectors that are orthogonal to this. We will show that f in fact does not contain any element outside of this hyperplane. So by absurd, if we do have an element that is not in the hyperplane, it is an element in f, this is also an element in f, so this difference is in f. So if I add it again, I obtain that this vector that we know w is also in f, but we see here that the inner product here is not negative. Here it was negative. So let us write this more explicitly. So we define w as the symmetric of z with respect to xf. It means that xf is in the middle. So we have this inequality, and if we consider w minus xf, so here we are left with only one xf minus z, it is exactly the opposite. So we have two quantities that are opposite and that both have to be negative. It means that they have to be equal to 0. So we have obtained that for all z, x minus f is orthogonal to z minus xf. Since this is true for all z, we obtain that x minus xf is in the orthogonal complement of f. We have thus obtained the decomposition x as the sum of an element in f and an element in the orthogonal complement. So let us reflect that this decomposition directly stems out of the theorem of projection on the closed convex subset. So the map that to a decomposition projects on xf will automatically coincide with this projection map. We have used, in fact, the projection on the closed convex subset to define the direct sum. But we can still notice, if we forget about this, if we just consider that we have a decomposition with two subspace that are orthogonal to each other, then we can notice that, so let me represent it like this, f orthogonal, every element in the Hilbert space decomposes with one component in f, one component in f orthogonal, and we see that the distance between this and f, by the Pythagoras theorem, it's square root of this square plus this square, and we see that it is minimized at this point. Here, this distance is bigger than this distance. So the smallest distance is norm square of f2, and it is reached at f1. And similarly here, the smallest distance between h and f orthogonal is reached at the point f2, and the distance is norm of f1. Moreover, we see that in this case, when f is a closed linear subspace, then the projection map is linear, and we can even show that because those two spaces are orthogonal to each other, it is self-adjoint. So next property, let us show now that when f is closed, then it is equal to f orthogonal orthogonal. Let us first show left-hand side included in right-hand side. So pick an element in f. It is orthogonal to every element of f orthogonal. This directly means that it is in the orthogonal of the orthogonal. So remember this, we'll use in the next point. Conversely, this space is a subspace of H. So an element x in f orthogonal has one component in f and one component in f orthogonal. Because it is orthogonal to every element in f orthogonal, it is in particular orthogonal to the second component. So inner product equal to 0. If I write expand x, x1 is orthogonal to x2, so we are left with the second component norm square. It means that x has vanishing second component, it only lies in f. So we have the inclusion f orthogonal included in f. Now, if F is not necessarily closed, we still have the same inclusion, so by the previous point, and we can say that the double orthogonal is the orthogonal of something, so it is closed. So we have space that is closed and contains F. If we recall the definition of the closure is the smallest subset that is closed and contains F. So we have another one. It means that the closure is smaller than F orthogonal. So we have the first inclusion. Second inclusion, we just use the fact that the orthogonal complement reverse the inclusion. So here it's reverse. We use it 2 times. So F orthogonal included in closure of F orthogonal. And now we use the previous point that this is a closed subset, so its double orthogonal is equal to itself. So we have the other inclusion. And last point, let us consider the decomposition of H as a direct sum of this closed convex closed subspace and its orthogonal complement by the point C. F orthogonal is equal to the closure of F. So we have this decomposition. Now, if F is dense, so the closure is equal to the whole Hilbert space, then the intersection is equal to F orthogonal itself, because everything is included in H, and it is reduced to 0 because they are in direct sum. Conversely, if F orthogonal is reduced to 0, then every element lies in F orthogonal, has trivial component in F orthogonal. As an exercise, let us take a minute to reorganize the arguments we have presented in order to reprove this last implication. So if F orthogonal is reduced to 0, then by definition of density, for any H in H, there exists a sequence in F which converges to H. Let us recap what we have established. So for an arbitrary subset, the orthogonal complement is always a closed linear subspace. And for a subset F, which is a closed linear subspace, then H decomposes as F direct sum with its orthogonal complement. And the canonical projection map on each component coincides with the orthogonal projection map of the first section. And in general, for a linear subspace F, the double orthogonal complement is equal to the closure of F. So if F were already closed, then F double orthogonal complement equals F. And lastly, one has a characterization of density of a linear subspace in terms of its orthogonal complement. So let me say a word about the proof in the finite dimensional case. So one here simply takes a basis of F and completes it into a basis of the whole space. And then by the Gram-Schmidt orthogonalization procedure, one obtains something even stronger than this direct sum, since one obtains a direct sum of subspaces of dimension 1, which are orthogonal to each other. So one can generalize this to infinite dimensional space with the help of the axiom of choice in the form of Zorn's lemma. So here one has to distinguish between direct sums of Hilbert spaces and direct sum of mere vector spaces. So in the first case, one would require the summand to be Hilbert spaces themselves, so they have to be complete, and as a subset of a complete space, it has to be closed. And moreover, the summand have to be orthogonal to each other. Whereas as a direct sum of spaces, vector spaces, then one only requires, in the case of two summand, that F intersection G equals to 0. So in the infinite dimensional case, one takes a basis of F, and by the incomplete base theorem, extends it to a basis of the whole space, and then obtains a direct sum. But one cannot require that G be orthogonal to F. And in fact, we see that when F is not closed, what happens is that F will contains element in F closure minus F. So this is not a vector space, it doesn't contain 0, and if you take an element in F closure minus F, and you add to it an element in F, you obtain again another element in F closure minus F. So what it means is that you can take a linear combination of elements in here, which are back into F. So when you are considering a basis of G, not only do you need to take linearly independent elements in here, but you need also to make sure that their linear combination doesn't fall back into F. So this subset is of course a subset of F closure, but we have seen here that this is equal to F orthogonal. So if you take an element that is non-zero, it will never be in F orthogonal since it is in its complementary. In fact, in the fourth section, we'll see that for any element in here, you can always find an element in F whose inner product with this element in F closure is non-zero. So let us now also mention the projection in the finite dimensional case. So if one chooses an orthonormal basis of F, so orthonormal basis of F, then one can give an explicit expression for the projection with the help of inner product. So EI x EI. So one should understand the infinite dimensional case as a generalization of this formula where infinite sums are allowed. So this is the content of section 4. Section 3, the Riesz representation theorem. So let me first state the theorem, then present the situation in other contexts, some similar, some different, in order to better appreciate the specificities of Hilbert spaces, and then prove the theorem. So we denote H prime, the topological dual of H, that is to say, the vector space of continuous linear forms or continuous linear functionals on H. The theorem says that the map which to a vector A associates taking the inner product with A is a bijection. It means that every continuous linear form can be written in this way. In fact, one can endow H prime with a Hilbert space structure using this map capital Phi, and we usually say that it is an isomorphism of Hilbert spaces. So there's an identification vector and a continuous linear map. So let me now start a rather long aside on duality that you may skip. We start with the most simple case of a finite dimensional space E with a basis E1, En. We define the dual basis B star of linear forms En. So in general, a linear map is completely determined by its value on the basis element. So let me first write an arbitrary map. So it sends E1, so we just give it a name to the value. It sends E2 to a certain value, lambda 2, and then En to lambda n. Then it is completely determined by taking a linear combination. So by definition, we define the first basis element, so first form, by the value on E1 is 1, the value on E2 is 0, and the rest is 0. We define the linear map epsilon 2 as having value 0 on the first vector, then 1 on the second vector, and 0 for the rest. So this corresponds to epsilon 2. And then for the last vector, epsilon n, it has value 0 everywhere, except on the last one where it has value 1. Usually we just would write it like this for all indices in integers from 1 to n. Epsilon I evaluated on ej is given by delta ij. And we see that our arbitrary linear form can indeed be decomposed as the sum from 1 to n of lambda I epsilon I. It is a unique decomposition. So lambda 1 times this vector, lambda 2 times that. So what it means is that we indeed have a basis of the dual space and it is of the same dimension. So we can define an isomorphism from E to E dual by mapping every basis vector to the associated dual element. So if we have, if here instead we have a linear combination, so from 1 to n, we have a column vector x1, xn. We usually will write it like this. It associates the line vectors. So this map maps column vectors to line vectors. But it depends on the choice of basis. But in this basis, it always has a matrix identity. So the matrix associated to psi with those chosen bases is identity n times n identity. So let us now assume that E has an inner product structure, but still with a given basis. So E1, En. N dual basis. Epsilon 1, epsilon n. We can define the Gram matrix, which encodes the inner product structure. So it has component Gij given by the inner product of the basis element. So it is a symmetric definite positive matrix, so invertible. And because the field, so R or C, is complete, finite dimensional spaces over R or C are also complete. So we are in the framework of the Riesz representation theorem. So we define the map of the theorem, and let us see what it does to a basis vector. So it maps it to this linear map. So let us evaluate what it gives on an arbitrary vector y. So it just gives inner product of y with ej. We then write the decomposition of the vector in the given basis, yi, ei, ej, and then by linearity of the inner product with respect to the first variable, it gives yi, ei, ej. And here we recognize the Gram matrix Gij, and this is the evaluation of a linear form on y. Indeed, if I take epsilon k and evaluate on this linear combination, it will give combination of here epsilon k ei, and this is always 0 except when I equals k, and then we're left with just the component. So just left with the component. What this means is that this linear map can be decomposed in the dual basis. So sum from 1 to n of Gij epsilon I. So this we can also write it as column vector. So it is column j. So first 1j in the direction epsilon 1. G2j in the direction epsilon 2, and so on. Gnj in the direction epsilon n. So this means, this is true for all j, this means that to each vector it associates a column of this matrix. It means this matrix is in fact the matrix of phi in the chosen basis. But we can confirm it by looking at what it does to an arbitrary vector. So this usually we can write it as a column vector, so x1, xn. Here I would also have the same combination, 1 to n, xj, here sum xj. What it does is that it's xj times a column, so x1 column vector times the first column, x2 times the second column, xj times the jth column, and so on. So we recognize here the matrix multiplication. So this is exactly what we have in Riemannian geometry or special or general relativity. So we usually would write only the components. So exactly like the column vector, we don't write the vector. So also with Greek indices, we don't write the basis vector, and it is mapped to in the Riemannian geometry. The grand matrix is called the metric, and it's also written with lower indices. And we have the Einstein's summation convention. So we have index low, index upper index with sum. It's exactly this sum over j of gij xj. And then we write it, the result. So this is just a notation. We write it with the lower index. So this is a component. So we see component in the direction epsilon mu. Here it should be epsilon mu, but we don't write the vectors anymore. So in this kind of notation, we just write the components. And what it does is that it takes a vector with upper indices to lower indices. So this is called contravariant vector, and this is called covariant vector. And because it lowers the indices, we call it flat. Like in music, it lowers the frequency. And so the inverse map, so this map is exactly this map. So in another context, so the inverse would just go from the dual to back to the space. Let us see what it does to a basis vector. So again, if I go back to this notation, it should give the column I of the inverse matrix. So if I write it as a sum, so from 1 to n, ek. Of course, if I write it as a column vector, so I would have g minus 1, component 1, column I, g minus 1, direction e1, g minus 1, line 2, column I, direction e2, and so on, g minus 1, line n, column I. And of course, if I have a linear combination, it's the same. Let me directly write it with the convention of physics convention or Riemannian geometry. So we have a lower index, and then it is mapped to, we don't write anymore the fact that it is the coefficients of the inverse matrix. So we just directly write with upper indices and then lambda nu. And this there's a sum over n, and we simply write it lambda mu. And so it raises the indices. So let me give the interpretation if we just look at the image of epsilon I. So let me call this vector ui. It is a vector and not a component. And what we know is that those two maps, flat and sharp, they are inverse of each other. So they give the identity when we compose. So this is the identity epsilon I. But this we see, we have denoted this vector ui to a linear form. It associates this vector, and flat just gives back a linear form, but in the form of the inner product. What it means is that the basis linear form can be obtained as an inner product. And in that way, the identity map from E to E, or identity, or we could also write the same for projections. So it just write x to an element, it gives its decomposition in a basis. So epsilon I x ei, you can write it with, thanks to this map, with the inner product. So I from 1 to n, and here you can write it as a form of inner product with ui, vector ei. So this is slightly different from what we are used to, because now we have to pinpoint the fact that this map from the theorem is independent of the choice of basis. When we have an inner product, we can define orthonormal basis, and in the case of orthonormal basis, then the previous construction, orthonormal basis, in that case, the previous construction coincides. If the basis is orthonormal, then the Gram matrix is just the identity, so it will map epsilon eg to epsilon, so ej will be mapped to ej, epsilon j And similarly, the pre-image of epsilon I is just EI. So here, when the basis is orthonormal, we have the usual formula. In the case of orthonormal basis, it does map a column vector to a line vector. We now move to the infinite dimensional case by considering a vector space with a countable basis. We illustrate in this particular example the fact that the algebraic dual, so the vector space of linear forms but without any continuity condition, has a dimension that is always infinitely bigger than the dimension of the original space. So in this example, we exhibit an uncountable family of linear forms that are also linearly independent. So the basis here is countable, and if we find a basis, it will be uncountable. So given a parameter ρ, let us consider the following linear map. So by definition of an algebraic or Hamel basis, an arbitrary vector is always a finite sum of basis elements, so x0, x1, x2, so on, and at some point it is 0. There are finitely many non-zero coefficients. And so to a vector, we associate the following real number. So this time, the parameter ρ to a certain power. And so as we have said, there are finitely many components, so this sum is a finite sum. We want to show that this family is free. So in the definition is for any linear combination, so of those linear maps. So for different parameters ρ, p, so let us consider a finite combination. We want to show that if such a combination is 0, then all the coefficients, integers from 1 to n, alpha p equals 0. We prove this by successively evaluating on the basis element. If I write it as a vector, so this is 1, 0, 0, 0. Here, component 1 is 1, and then the others are 0. And so we do it up to n minus 1, 0, 0, 0, and position n minus 1, 1. So if I evaluate such a map on this vector, so the only non-zero component is x0. So a1, ρ1, power 0, and then plus alpha 2, ρ2, power 0, and so on. Alpha n, ρn, power 0 equals 0. If I evaluate on this vector, so the first term is 0 and the non-zero term is ρ to the power 1 plus alpha 2, ρ power 2, power 1, plus and so on, plus alpha n, ρ n, power 1. Similarly, next term, alpha 1, ρ 1, power 2, plus alpha 2, ρ 2, power 2, and so on, equals 0, alpha n, ρ n, power 2. We stop at power n minus 1, ρ 1, power n minus 1, plus, alpha n, ρ n, power n minus 1. So we write this system in matrix form, and so we recognize, so 1, 1, 1, 1, ρ 1, power 1, ρ 2, power 1, ρ n, power 1, ρ 2, power 2, ρ 1, power 2, ρ 2, power 2, ρ n, power 2, and then we stop at ρ 1, power n minus 1, ρ n, power n minus 1. Evaluated on the vector alpha 1, alpha 2, alpha n equals 0, 0, 0. We recognize the von der Mond matrix, and so for different parameters, this matrix is invertible. The determinant is non-zero, so the kernel is reduced to 0. It means that all the coefficients are reduced to 0. This is 3.00. So when E has some topological structure, we only consider the topological dual, which consists of continuous linear maps forms. So let me give a few more examples. So let X be a measurable subspace that is sigma finite. So it is can be written as the union of subspace of finite measure. And so for P, a real number greater than 1 can consider the spaces of LP functions, so functions with value in R or C that are integrable, so whose power P, so modulus or absolute value, is finite. In fact, this condition ensures that this space is in fact very, very similar. It's the same as the space of sequences in the sense that it will have a countable basis, Schauder basis, so where infinite sums are allowed. Un power p, n sum over n is finite. So when we have p and q real numbers greater than 1 that satisfies a conjugacy relation, then we may do another video to prove these kind of properties. The topological dual of LP space is in fact LQ, and topological space of the sequences is LQ sequence. So they are still not the same, but pretty similar. And in fact, when P equals 2 equals Q, we are in the case of Hilbert space, where the dual is equal to the initial space. So let me give two more examples. So again, another one where the dual is very different. So if we consider the space of smooth functions with compact support with a certain topology, then the dual is known as a space of distribution, and they are very different. Distribution. So you see that the distribution does not come from a smooth functions, but you can have special case of distributions, spaces of distribution which are dual to each other, namely the so-called Sobolev spaces, which are Hilbert spaces, denoted HP. Also, I invite the viewer to come back to this LP example after the proof to see what argument fails in the case P and Q different from 2. So let us now prove the theorem. So first of all, we notice that for any vector A, the map which to Y associates inner product with A is indeed a continuous linear form, so an element in H prime. So linearity comes from linearity of the inner product with respect to the second variable, and continuity comes from the Cauchy-Schwarz inequality, as we have already seen. So linearity of the inner product with respect to the first variable will yield the linearity of capital phi. So let us now show injectivity. Consider an element in the kernel, so such that phi a gives 0. We evaluate precisely on the vector A. It gives inner product A with A, and by positive definiteness of the inner product, it means that A has to be 0. So in the finite dimensional case, this would be over because we had already seen that a basis of the dual has the same cardinality as the basis of the original space. So we have a linear map that is injective between two spaces with the same dimension. So in infinite dimensional case, this is not sufficient. So we still need to show that any vector comes from a vector. Any linear forms comes from a vector and can be written as an inner product. So if we're considering the 0 linear map, then you can obviously obtain as inner product with 0. Otherwise, the kernel of this linear form is not the whole space. Moreover, it is a closed linear subspace, closed as a pre-image of a closed subset. So because it is not the whole space, the orthogonal complement, so first of all, it exists because this is a closed linear subspace, and the orthogonal complement is not empty, not reduced to zero. So there exists an element such that L of A is non-zero, and we now want to show that it generates the whole space. So it suffices just to show one inclusion, since A is an element of the orthogonal. So let us take an element in a kernel orthogonal and consider this linear combination. It is precisely such that when you evaluate the linear map, here it gives LV, here it gives LA, so it simplifies, and we are left with 0. It means that W is both in the kernel and in its orthogonal complement. So it is 0. This means that V equals a coefficient times A. It means that it is in the span. So if we choose the correct factor, we want to show that then the linear map can indeed be written as inner product with this vector. So we check it on both summand. On the kernel, so B is in the orthogonal of the kernel. So naturally, if we do the inner product with X, it gives 0. And for an element in the orthogonal of the kernel, we have seen that X has to be proportional to A. So if I evaluate this inner product by bilinearity, I take out every coefficient. I'm left with inner product of A with A. It simplifies then with the norm of A squared. And then I put the lambda back into L of A by linearity of the linear form. And here we recognize X. So we have phi of X equals L of X. So we have checked that those two maps coincide on both summands, so on the whole Hilbert space. Let us now see how the Riesz representation theorem serves in the definition of the adjoint. So let U be a bounded operator. Its adjoint U star is characterized by the following relation denoted 5. So U of X inner product with Y can be written as inner product of X itself with something. So we notice that this relation is symmetric. So U star is the adjoint of U, but U is also the adjoint of U star. So as a consequence, their operator norms coincide. And we recall that the operator norm is the supremum of the operator on the unit sphere. So for a fixed Y, let us consider the map which to X associates inner product of U of X with Y. Since U is continuous and the inner product is also continuous with respect to the first variable, this is indeed a continuous linear form. So by the Riesz representation theorem, it can be written as inner product of X with a certain vector. We define the adjoint as the map which to Y associates A index Y. Let us now show that this is linear, so we consider a linear combination here of Y1, Y2. So again, by the Riesz representation theorem, the map which to X associates this inner product can be written as inner product of A of X with this vector. Then by linearity of the inner product with respect to the second variable, it expands as follows. Then this factor, again by the Riesz representation theorem, can be written as inner product of X with AY1. And similarly, this factor can be written as inner product of X with another vector. Then, by the linearity of the inner product with the second variable, it can be written again in the same form, inner product of X with this linear combination. We now recall that in the Riesz representation, the linear map which to A associates this linear form is injective. It means that if those two linear forms coincide, then they are induced by a same unique vector. So we have equality here of those two vectors, and by definition, this is U star of this linear combination, and this is linear combination of U star Y1, U star Y2. So this is linearity of U star. Let us now show that it is bounded. We compute this norm square. So by definition, this is this inner product. And now by the relation 5, we consider this as X and this U star. This is equal to U of X inner product with Y. Now, by the Cauchy-Schwarz inequality, we obtain this. And then by definition of operator norm, this is smaller than operator norm of U times the norm of what is inside. Now, if this quantity is equal to 0, then 0 is smaller than this product. And if it is different from 0, we simplify. We thus obtain norm of U star Y smaller than operator norm of U times norm of Y. Then we take the supremum for Y in the unit sphere, and we obtain thus operator norm of U star smaller than operator norm of U. We now recall that the relation phi is symmetric. U is the adjoint of U star, so its operator norm is smaller than operator norm of U star. We have thus the equality. A few additional comments. So in the finite dimensional case, if we have an orthonormal basis, then we plug in the relation x equals ej, y equals ei. So u of x is the jth column of u, and then inner product with ei, it yields the component in line I. Similarly, here it's the eth column of u star, and now the component in line j. So the matrices of U and U star in the orthonormal basis are transposed to each other. Last comment about the adjoint. So in the general framework of topological vector spaces, the adjoint of a linear map sometimes refers to the map which to a linear form on S associates the following linear map on E, which is given by composition on the right. So here, in order to distinguish, we'll call this the dual map to phi. So we have the following relation between our definition of adjoint and the dual map that we denoted here with a tilde. So U star and tilde. Let us check it on an arbitrary vector. So capital phi maps a vector to the following linear map, so which is taking the inner product with y, and then we precompose with u. So here is a variable, and so we first apply u and then take the inner product with y. And then phi minus 1 says that there exists a unique vector such that this linear map can be written as inner product of the vector with u star of y. We recognize exactly condition 5. So up to now, we have seen the projection theorem on a closed convex subset. So for any x, there exists a unique point in C, which minimizes the distance between x and C. It is such that for any z in C, inner product z minus xc with x minus xc is negative. So in the special case where C is a closed linear subspace, then for any x, x minus its orthogonal projection is orthogonal to C. So C is in the hyperplane, or the inner product is equal to 0. So the Hilbert space decomposes as the subspace direct sum with its orthogonal complement. So an important application of this is the Riesz representation theorem. So for any continuous linear form, the kernel is a closed linear subspace. So the Hilbert space decomposes as kernel direct sum with its orthogonal complement. So if L is non-zero, then the orthogonal complement is a one-dimensional subspace, and by the correct choice of size, so of normalization of the generating vector, the continuous linear form can be written as inner product with A. So let us now address the notion of orthonormal basis or Hilbert basis. Let En be a countable family of orthonormal vectors of H, and let capital F be the linear subspace it generates in the algebraic sense, so by finite linear combinations. We will see concretely that F is not complete, but an abstract argument is provided by the bare category theorem. Indeed, a consequence of it is that any infinite dimensional complete normed vector space, so any infinite dimensional Banach space, cannot admit a countable algebraic basis. So there's a contradiction between infinite dimensional complete and countable basis. And if we complete En into an algebraic basis, then we observe that the additional vectors cannot be orthogonal to the En. Indeed, we have seen that the elements in the closure are in the orthogonal to the orthogonal, so they are not in F orthogonal. In other words, there are infinitely many new directions, so linearly independent vectors, but none of them are orthogonal to the En. This family is in fact already maximal for orthogonality. What this means is that there is no orthonormal basis in the usual sense, so in the algebraic sense. So one may wonder, how does an element in F closure looks like? And the trick is to look at the projection operator, since any element in the closure can be written as projection of itself. And thus, a fortiori, any element in the closure is the projection of a vector in H. Let V be a vector in H, and for any integer n, let lambda n be the inner product of En with V. We will show that the series lambda n En converges. If we denote W its limit, then W is the orthogonal projection of V onto the closure of F, and its norm is smaller than the norm of V. We start by showing that a partial sum up to n is the projection of V onto the finite dimensional subspace generated by E0, E1, E2 up to En. Indeed, the projection, so left-hand side, is characterized by the fact that V minus projection is orthogonal to En. So in particular, it is orthogonal to the generating vectors. Then by linearity of the inner product with respect to the first variable, one obtains that the component of V is equal to the component of the projection. So the projection and V have the same decomposition, the same components. Then, since the Ek is an orthonormal family, one has by the Pythagorean theorem that norm squared of a sum is the sum of the norm squared. And then, since each Ek has norm 1, this reduces to sum of lambda k squared. Similarly, for each n, V decomposes as an element in En and an element in the orthogonal complement. So by the Pythagorean theorem, norm squared of V is a sum of two positive elements, so it is greater than norm of the projection squared. Now, as a sequence of n, this is a sum of positive elements, so the sequence is increasing. So this is equal to this. N is bounded by norm of V squared. Then since R is complete, a bounded increasing sequence admits a limit. The sequence is thus Cauchy. It then follows that the sequence of projections is also Cauchy. Indeed, again, by the Pythagorean theorem, norm of projection on EP minus projection on EQ squared is equal to this sum. Take the square root, and this can be made arbitrarily small because this sequence was Cauchy. As a Cauchy sequence in a Hilbert space, the sequence of projection admits a limit. Then, by continuity of norm squared, limit of norm squared equal to norm squared of limit. Let us now finally show that W is a projection of V onto the closure of F. We now use a property that we have mentioned, that if we are orthogonal to a set, then we are orthogonal to the closed linear subspace it generates. So here we just need to show that V minus W is orthogonal to the generating family of vectors of F and of F closure. Now, if the family generates a vector space that is dense in H, the family is said to be total, and if H admits a total family that is countable, then it is separable. In that case, V is equal to what we had denoted W, and norm squared of V is norm squared of W, so sum of lambda k squared. So here the modulus is not necessary, it's just for the complex case. So proof. This means that E is equal to the whole Hilbert space, so the projection is just the identity. Clearly, if V is already in the closed convex subset, then the point that minimizes the distance to V is V itself. And we have seen that it can be written as the limit of a sequence of projection on finite dimensional subspace, projection which take this form. So if we have a total family that is also orthonormal, then it is called a Hilbert basis or orthonormal basis. Final comments: if one has a countable Hilbert basis, then any vector decomposes in a unique way as a possibly infinite linear combination of the En, with the condition that the series of their components squared is convergent. So given a Hilbert basis, one has an isomorphism between vectors and the square summable sequences of their component. And the vector space of finite linear combination corresponds to sequences with finite support, whereas the closure corresponds to L2. So in general, one can show with Zorn's lemma that there always exists a Hilbert basis. So chapter 4, page 109 in the French edition. But if the Hilbert space is not separable, then the Hilbert basis is not countable. So here is the definition of a sum over an uncountable family. So for all epsilon strictly bigger than 0, there exists a finite family of indices, so k, such that for all finite family containing k, sum for I in L minus sum for I in k is smaller than epsilon. So what this means is that any finitely extra contribution, so with finitely many terms, is small. And the square summables condition here comes from the orthonormality of the family EI. So one can show that although this family is uncountable, every time you pick a vector, the family of non-zero components is always countable.